Okay, so we are continuing our look at section 6.3 on vectors. Everyone has their notes out. We were talking at the end of last class about unit vectors, so let's pick up where we left off. Unit vectors, which you cannot see what I'm talking about. Here we go. That assignment was not for you. Here we go. Unit vectors is going to be any vector with a magnitude of 1. It is often helpful to find a unit vector that has the same direction as a given non-zero vector. And to do this, we will divide vector v by its magnitude to obtain the unit vector, and we'll call it vector u. We often use vector u to represent the unit vector. So if u is the unit vector, we can find that by taking vector v divided by its magnitude. And that's the same thing as saying 1 over the magnitude times v. So this is, let me just get to this. This is a unit vector in the direction of v. This gives a unit vector in the direction of v. So u is the scalar multiple of vector v, and it's going to have a magnitude of 1. Do you have your gift out that we were working on?
Yes.
Okay, so I believe this problem is on your gift. Is that true? All right, so find a unit vector u in the direction of vector v, which is the vector 7, -3, and verify that the result has a magnitude of 1. All right, so in order to do this, let's get a visual of what we're trying to do here. We are given vector v, which is the vector 7, -3, which would put us right here like this. So here's vector v, boldface v. And we want a unit vector that's heading in that same direction. So I'm looking for a vector that has only a length of 1, but is going in that same direction. And we're going to call that vector u, boldface u. All right. To find that, we first need to find the magnitude. We need to find the magnitude of vector v. So the magnitude we find, remember the square root of, what's going to be the square root of what? All right, 7 squared plus a -3 squared. So we're going to get square root of 49 plus 9, which is square root of 58. So that's the magnitude. That's the length of my original vector v. All right, and we are going to find the unit vector then. Unit vector u. Unit vector u is equal to 1 over the square root of 58 times my original vector v, which was 7, -3. All right, so my unit vector is going to be, you could think of it as 7 over square root of 58, comma, -3 over square root of 58. That's our unit vector. It goes in the same direction as vector v, but it has a length of 1 or a magnitude of 1. Questions on how we got this?
Do you have to get the radical out of the denominator or no?
You could get the radical out of the denominator and simplify and write it as like what, 7 square root of 58 over square root of 50, or 7 square root of 58 over 58, and so forth. Steph? Awesome. We want a magnitude, we want to verify that the magnitude of vector u is equal to 1. Verify that the magnitude of vector u is equal to 1. Right? So how do you verify this? To verify, we're going to find the magnitude of our unit vector here, what we think is going to be a unit vector, and that's going to be the square root, yes? Square root of 7 over square root of 58 squared plus -3 over square root of 58 squared. Does this look correct? All right, and so when we do this, we end up getting square root of what, 49 over what? 49 over 58 plus what? And what's 49 plus 9?
Oh, 58.
58 over 58,
That's 1.
which is just square root of 1, which is 1.
That took it out every time.
No, but I think it's good to know where this is coming from and to know that, yes, this really does work. This really does give us a unit vector. Are we okay with this?
Yes.
Awesome. Okay, so now we are going to switch gears a little bit and talk about standard unit vectors. Now we understand that a unit vector has a magnitude of 1. But if we're talking about the standard unit vectors, then we're talking about little vectors that are horizontal or vertical and are 1 unit long. So if the magnitude of this little vector is 1 and it's going to the right like this, it's a standard unit vector in the horizontal way. And if this vector, that's supposed to be going straight up and down, so it looks a little bit crooked. All right, that one, if that has a length of 1, then it is the standard unit vector J. Agreed? All right, that's the idea with this. And so that means that this vector would have the name 1, 0, right? We call it I, right? But that would be in, what do we call that form when we use these vector braces? Component form. So the component form of this standard unit vector would be 1, 0, and the component form of this standard unit vector would be 0, 1. All right? We use the bold-faced letter I to represent this little vector that's pointing to the right, and we use the bold-faced letter J to indicate this vertical vector 1. Have we talked about the imaginary unit yet in this class? Okay, we're going to get to that. In chapter 2 is where we're heading next. All right, chapter 2 is on polynomial functions, and we're going to be solving quadratic equations. And sometimes when you solve a quadratic equation, you get a negative number under a radical, right? And that gives you an imaginary number, and we'll talk about that. And the symbol for the imaginary unit is also I, but I don't want you to get confused. That I has nothing to do with this I. All right? Okay, so boldface I and boldface J can be used to represent any vector V in component form, V1, comma V2. In other words, we could write V1, this first component, times that standard unit vector that goes to the right, 1, 0, plus V2, comma, the standard unit vector that goes vertically. And we could write this as V1, comma, V1I plus V2J. This would be considered a linear combination of our standard unit vectors, I and J. Was this on your homework?
Yeah.
This one? Yeah, I think I gave you one like this. Okay. And if you didn't understand how to do it last time, you're going to be okay with it now, I hope. All right, so let's take a look at this example. Is this on your gift? Let U be the vector with initial point negative 2, 6 and terminal point negative 8, 3. Write U as a linear combination of the standard unit vectors, I and J. So let's get a little visual of what's going on here. Sure.
Are we having a separate test or 6-3 or just only a 6-3 quiz?
That's an excellent question.
Does have an
I think that I will probably make our test on 6-1 to 6-3 and then maybe a few sections in chapter 2. But we are going to have a quiz on 6-3 next week.
We won't have a test for a little bit.
Yeah, I think a week or 2, yeah.
That's not.
Okay, so let U be the vector with initial point negative 2, 6. Negative 2, 6 is right here. And the terminal point is at negative 8, 3. All right, so this vector looks like this. all right? And I'm asking you to write vector u as a linear combination of the standard unit vectors I and j. So what I'm hoping that you are going to be gathering from this is that my standard unit vectors, I really have to go, well, I tell you what, let's put this in component form first. What's the component form of vector u? Do you remember how to do this? All right, because we do terminal minus initial, right? Comma, terminal minus initial. So this is going to be -8 minus a -2. Agreed? And then what? 3 minus 6. So I end up getting, in component form, -6 comma -3. Everybody agree? Okay, which basically just means that this whole vector could have been written or drawn right here with the initial point at 0, 0, and it's going to end up at the point -6, -3. True? Okay, but we are not asked to talk about that. We are asked to write this as a linear combination. Remember, what we can do is we could just say this -6 right here times the horizontal vector, standard unit vector, 1, 0, and this -3 times the standard unit vector that points vertically. So that means we could write this as -6 boldface I plus a -3 boldface j. This is a linear combination of the standard unit vectors I and j. And what I'm hoping that you're going to take away from this is that every time I have a little unit vector that's 1 unit long, you with me? That points to the right, that's I. But each of these is pointing to the left. And how many of these do I have? 6. And they're negative, right? Because they're going to the left. So that's why I got -6 times my standard unit vector that goes to the right. Does that make sense? And then I know that from this point, I need to go down how many times? 3 units. So that's J is the one that points up, but I want to go down, so that's why I need a negative, and I need 3 of them. Does that make sense?
Yeah, I like showing the slope.
Well, sort of, because you're showing how can I get from this initial point to this terminal point by combinations of my little standard unit vectors. Like how many times do I need to take my little vector that goes to the right? How many times do I need to take my little vector that goes up, right? Does that make sense?
So you only need to so say this was problem or this or whatever.
Yeah.
Our answer would just be -6I plus -3j.
Yes.
Our work can be as simple as just looking at graphs.
Yes. Yeah, I mean, I think you'd want to probably put it into component form first and then go from there. Okay, questions on this? All right. Okay, so let's take a look at this, please. Focus. Let U be equal to standard unit vector I plus standard unit vector j, and let V be 5 times I minus 3 times j. To find, you'd have this one? No. All right, let's just take a look and listen.
Yes, we no. Number 7 is the same as number 6.
So should we just like cross it off right from this one?
Just throw this one on your notes if you don't have this one.
Wait, 6 and 7 are.
Sorry about that.
We already established that.
Shots?
So for this one, if you're trying to find 2u minus 3v, you could write u as obviously just I plus j, and minus 3v is minus 3 times 5I minus 3j. Everybody with me?
Yeah.
So far, so good?
Yes.
By the way, I hope you're picturing, what unit vector, well, what u would look like. I shouldn't say unit vector. It's really just the vector that goes 1 unit to the right and 1 unit up. So it's really this vector right here. Does that make sense? And vector v would be the vector that is 5 of these little guys to the right. 1, 2, 3, 4, 5, and then 3 down. 1, 2, 3. You with me? So we're really talking about this vector is vector v. Make sense?
Yeah.
Okay, so we're now taking 2 of these vectors and subtracting off 3 of these vectors. All right? And that's going to give me, if I distribute, I get 2i plus 2j minus 15i plus 9j. Everybody with me? And I combine my like terms and I get negative 13i plus 11j.
That's our answer?
Easy.
So if I wanted to find 2 vector u minus 3 vector j, it would turn out to be negative 13i plus 11j.
Question. What does I stand for?
This I, boldface I, stands for the standard unit vector that points to the right. So for example, on this graph, this vector right here would be boldface I. All right? Boldface J would be this standard unit vector that points straight up. So this is standard unit vector J. Does that make sense? Okay. All right, so we're good with this one. I think that was it for this page. All right. Now, as Maria noticed last class, there is going to be a connection between unit vectors and the unit circle, right? All right, so let's talk about this connection. Direction angles. If vector u is a unit vector such that theta is the angle measured counterclockwise from the positive x-axis to vector u, then the terminal point of vector u is going to lie on the unit circle. All right, so let's get a visual. We got our unit circle here, and let's say here is our vector. All right, let's say it's in standard position, so it's got its initial point at 0, 0. We're talking about this angle right here being angle theta, right? And we know it's a unit circle, so we know this point right here is 1, 0. We know this point right here is 0, 1, and so on. True? Okay, so the idea here is this. This ordered pair right here, we know, we'll just call it x comma y. And we know that x is really the cosine of theta. Agreed? And we know that the y is the sine of theta. Yes? So we could say that this vector u, right here, vector u, which is a unit vector, has a direction angle of theta, as we would say, and it has its terminal point at x comma y, or we could say its terminal point is at cosine theta, sine theta, which is why we can write it with the cosine theta, sine theta in the vector braces. In component form, that's what it would be. Agreed? Does that make sense? In component form, this vector right here would be cosine theta, comma sine theta. Because that's going to be the end point, right, the terminal point of that vector. Right? All right, and we could say then that that's the same as cosine theta times I plus sine theta times j. We're describing how far to go to the right and how far to go up. And you know all of this from like way back, chapter 4 stuff. All right, that the x is the cosine of theta and the y is the sine theta on our unit circle.
So theta will you're not gonna give us a problem like that. Theta will be like an angle measurement.
Theta is going to be the angle formed, right, by your vector.
Okay.
Okay? So, the angle theta is the direction angle of vector u. And if vector v, this should really be boldface, and this should not be caps. If vector v is a vector that makes an angle theta with the positive x-axis, then it has the same direction as vector u, boldface. And you can write it as vector v equals magnitude of vector v times cosine theta, sine theta. In other words, this is how we're still going to talk about direction angles, but get off of the unit circle. We don't have to be a point We don't have to be an angle that has its terminal point on the unit circle. We could say, oh, you know, I want to have a vector that looks like this and has its terminal point out here. Well, I can still describe that vector using cosine theta and sine theta. I just have to take the magnitude of that vector and multiply it by my unit vector cosine theta sine theta. So if I took the magnitude of vector v and multiplied that, then I would be describing this vector v that extends past the unit circle. Okay, so that's why I have magnitude of vector v times cosine theta comma sine theta in vector braces, or I could write cosine theta sine theta as cosine theta I, and I can write the sine theta here as sine theta j. Okay, so A is going to equal the magnitude of vector v times cosine theta, and B is going to equal magnitude of vector b times sine theta. All right? So the tangent of theta is going to be, we know that's equal to y over x, right? You remember this? Tangent of this angle theta is the y over x. Agreed?
Yep.
All right, so tangent of theta is y over x. That's the same as saying the sine over the cosine. But the sine of theta is b, if I solve this equation, b over magnitude of v. That's the sine of theta. And if I solve this,
Where did we get A?
A and B would be like this point right here. All right, sorry about that. That would be AB. So A is going to be the magnitude of V times cosine theta, and B would be the magnitude of V times sine of theta. So if I solve for sine of theta, I would have to divide both sides by magnitude of V, right? So I would get sine of theta equals B divided by magnitude of vector V. And what would A be equal to? I'm sorry, what would cosine of theta be equal to? All right, so I get cosine theta equaling A over the magnitude of vector V. And so when I'm trying to find tangent, I know tangent is sine over cosine, so that's going to be B over magnitude of V divided by A over magnitude of V, and that's going to simplify to just B over A. This is how we're going to say, you know what, I've got, well, we're going to look at an example in just a minute, but let me just give a quick one right here. Let's say I have a vector that ends up with its terminal point here at, I'm going to say negative 5, 6. All right, so I could describe this vector in component form as negative 5, 6 in vector braces, right? And I could find this angle. I can find that angle by using the formula tangent of theta is equal to B over A. So tangent of theta would be 6 over a negative 5. You with me? And then I can find, you know, theta is going to be tangent inverse of 6 over negative 5. The only thing you need to watch out for is what quadrant you're in, because that will make a difference with your angle. And we'll talk about that in just a minute. So I think this example is on your gift, maybe? Yes? No?
Yes.
Okay, so the question is, find the direction angle. This vector right here in component form could be written, what? Well, it's really negative 6i plus 6j, boldface I, boldface j, right? So in vector form, it would be what, comma what? Negative 6, 6. So in this case, it's ending up at the point negative 6, 6. So we could say, what do I have here? That A is negative 6 and B is positive 6. True? If that's the case, then we could say that the tangent of theta is going to be B over A, which would be 6 over negative 6, which is negative 1. Correct? So, do you know what angle? I mean, this one I don't even think you need your calculator for. This one's on your unit circle. Where is the tangent equal to negative 1? Negative where? So down here, you're saying negative pi over 4. So up here would be what? 3. So it's going to be 3 pi over 4. What about degrees?
It would be, that's 90.
So 135? Does that sound right? So 135 degrees would be this angle. Are we okay with this? Yes.
I thought like when you took arctangent, you were like running backwards. But you're not doing that. You're not doing that.
Well, no, Rachel's got a good question. Let's talk about this. Let's say you are going to do this on your calculator. Let's see what our calculator gives us. Theta equals tangent inverse of negative 1. True? So what does your calculator say theta is equal to?
0.7. Oh,
I got negative 0.7853.
Negative 0.78. Okay, that's what units?
Radians.
Convert to degrees, please.
Negative 45.
Negative 45. So in other words, you're right, Rachel. It is going to give you an angle measure between negative pi over 2 and pi over 2. However, we need to adjust because we see our angle wrapping into the second quadrant, not down here into the fourth quadrant. Does that make sense? So you have to kind of be smart and look at your picture to figure out what the true angle is. Does that make? You can't just blindly trust your calculator. You got to be looking at the picture also, right?
Right.
So your calculator is going to give you this angle of negative 45 degrees, but you got to say, I don't want that one. I want the one that is supplementary to it, right? Which is 135. So that's why our angle is going to be 135. All right. Good question. Thank you for bringing that up. Where? Thor. There it is. I sure do.
Who's Thor?
What? How many do you have?
Where is he from?
What do you mean?
Where
Where is he from? You haven't seen this
Asgard.
movie?
Of course.
Thor.
Thor's planet.
I've never seen that. I've never seen that.
Thor is so good.
What is Thor?
You know, if you don't know who Thor is, that's making me Thor. Okay.
Wow.
Okay.
That's a good one.
All right. Let's try this one. All right. Is this example on your gift? All right. Try this one, please. Vector V is negative 7I minus 4J. And I'm asking you to find what is A, what is V, what's tangent of theta, and then use your calculator to find theta, the direction angle for this vector, which I have marked in the picture. You see it's going into quadrant 3, so we'll be thinking about that when you are using your calculator. So in this case, what is the A equal to? A is negative 7, and the B is negative 4. So this ordered pair right down here is negative 7, negative 4. All right, so the tangent of theta is going to be what? Don't we want B over A? So negative 4 over negative 7, which is 4/7. So how do we find theta? All right, so we want tangent inverse of 4/7, and that turns out to be what? Calculators. 0.519 radians. Convert. Do people agree with Megan? Okay, and is that our answer?
Had to add one, right?
Add one. So in other words, 29.7 would be this angle, 29, right here. But we want to add 180 to that. So I need this plus 180, and that gives me what? 209.74 degrees. Is this okay? All right.
So we have at least half an hour to.
All right, so you don't want to get into the airplane example?
No, I think we'll save it.
All right, we'll save the, what else do we have? Just a quick,
Yeah, we
peek.
just have an airplane.
we have an airplane example, that's it? Don't you?
Two airplanes.
2 airplanes? Okay,
We got 2 airplanes.
2 airplane examples, all right. So we'll take that up next time. Meanwhile, you are going to be, I'm going to stop this video now. And we're going to be collecting homework and taking our quiz.
We do.